Okay, let's talk about SMAW Basics. Okay, so when we talk about SMAW, or as some people call it, stick welding, first of all, we need to know what this acronym SMAW stands for. Because whenever you hear it in the industry or it's specified in a welding sheet or talked about in a textbook, it's going to be called by the proper name, SMAW. So it's an acronym. It means it stands for Shielded Metal Arc Welding. Okay? SMAW stands for Shielded Metal Arc Welding. Okay, so we've kind of gone over the basics of how the welder's set up, but I have it drawn on here. We have our welder, our power source here, hooked up to our positive lead. We have our electrode holder, sometimes called a stinger. Coming out of the electrode holder back to the welder, this is our welding lead. Coming out of the negative, some people call this a ground clamp. Technically, it's not a ground clamp. This is our work lead. And our work clamp. The reason we don't call it a ground clamp technically is, especially with stick welding, we can switch these to, depending on which rod we're using or what we're welding, we can actually switch those, and so that the work lead can actually be a positive instead of a negative, which would be considered a ground. It's technical. A lot of people still call them ground clamps, but the proper name is the work lead and the work clamp. Okay? In our electrode holder, which this drawing isn't to scale obviously, but this is our electrode. We'll talk more about electrodes in the next section. On the electrode is a coating, the flux coating. Okay, down here we have our base metal. Or our workpiece, either one. Back here we have our bead. On top of our bead, we're just going to label all this out and then we're going to talk about it. Slag. This little cloud right here going around our weld is our shielding gas. The red droplets here, metal droplets. The molten metal here, that's our weld pool or puddle. Okay, I think we have everything labeled. So let's talk about what's going on here. So we have our electrode hooked to our electrode holder going to our welder. Let's just say we're running DC EP for this rod. We'll get more into what that means later in the electricity section. But basically, it's direct current, electrode positive. Okay. The rod is creating an arc. So when we touch it to the metal, so we have our metal here and our rod. We touch it down or strike it like a match and bring it back up, and that arc pops across. Now an arc is when electricity jumps across a gap of air, or it could be vapor. So we get the electricity jumps across from the base metal to our rod, or from the rod to our metal, depending on what polarity we're running, and creates that arc. Okay, and like we talked about earlier, the reason the rod melts is because air is not a good conductor. Okay, a conductor is anything electricity passes through easily. So metal is a good conductor. Water, we're a good conductor. Anything that electricity won't pass through very easily, say like wood or metal or wood or rubber, anything like that, that's an insulator. So air is not a good conductor. So when that arc jumps across and is going through the air, it creates a lot of resistance. And we'll talk more about resistance later, but basically that electricity is working really hard to get across that air because the air is not a good conductor. And that resistance in electricity, the resistance equals heat. And there's a lot of heat. When this melts, we're producing anywhere from 6,000 to 10,000 degrees Fahrenheit. That's really, really hot. So it melts that rod. Little metal droplets go down onto the plate or onto our base metal. I've got our arc length here. I've drawn it quite big. Usually you have that rod down tight in there, but I have it drawn so you can see the metal droplets. So the resistance melts the rod and deposits the metal onto our base plate, melting our base metal to our filler rod, or to our bead, creating a weld bead. As the rod melts and burns, the flux coating, the white stuff on the outside, or sometimes it's red, black, the coating on the outside of the rod also burns and melts, and it does a couple different things. The main thing it does is creates this gas cloud around our weld pool. Okay, so we need to protect that molten metal while it cools and solidifies. So it creates this gas cloud of CO2. Okay, when that burns, creates a gas cloud of CO2, and it's shielding the molten metal from the atmosphere. So in the atmosphere, if you think about it, there's quite a few different gases. A couple of the major gases in the atmosphere are oxygen and nitrogen Okay? So nitrogen and oxygen are trying to get in there and get inside that weld pool, that molten metal, and get in there and contaminate it and create what's called porosity. Porosity is bad. Okay? Porosity, if you have it in your weld bead, it's going to weaken it. If you're welding something structural and they x-ray it, you're going to fail your x-ray test and you're going to have to grind it all out or gouge it out and re-weld it. Okay, so like if we look at, let's say we're welding this corner here and we have our weld bead here and we didn't have good shielding, whether our flux was knocked off our rod or our rod angle was really extreme so we weren't getting that shielding, and we let porosity happen. We let that nitrogen and oxygen get inside our weld bead and create little air pockets. Well, now that weld bead, which we need to be really strong, is now compromised and is not going to have full strength. Okay, so shielding gas prevents porosity, which is good. Okay, the second thing the flux does when it melts, well, let's draw this out real quick. Try to help you visualize this. This is kind of the way I think about it. Let's say we have our weld bead here. Okay, when that flux melts into our weld bead, it has chemicals in it that they call scavengers. Okay, so the way I think about it is if you have this, if you imagine this as a lake, you have your boat here, and I don't claim to be an artist, guys. Okay, let's say in our weld bead we have impurities. We have some nitrogen, we have some oxygen, maybe we have some rust, rust or oil contaminants that we don't want inside our weld bead. Well, the flux helps clean that metal. It helps get that rust and oil out. It's kind of like you have a guy up here on the top of the weld bead and he's dropped down a rope with a bucket in it, and you got a little scuba diver down here, and don't forget to draw his little fins. He's down there in the weld, the scavenger is down there in the weld bead, throwing all those little impurities in the bucket. He brings them back up to the top. All of this happens within a couple seconds. Purifying the weld, cleaning it up, getting all those impurities out, bringing them up to the top. Okay? So if we get rid of our boat, our scuba diver, we now have all those impurities that the scavenger went in and got, and they've all floated to the top of our weld bead or lake, and we have this crusty part over the top of our weld bead. That is our slag. Okay? So we have our slag. Slag also helps protect the weld bead. So as it cools, this is still really hot right here. Maybe less and less and less as you go along. As the weld bead's cooling, that slag forms over the top of that weld bead and also protects it from the atmosphere, nitrogen, oxygen, other gases in the atmosphere. Okay. One more thing we need to talk about. It's another acronym. Okay, like we talked about, different rods for different applications, different electrodes. They run on different polarity, whether that's DC, EP, DCEN, or alternating current. There's different rods which we'll talk about, like a 7018 or a 6010 or a 7024. There's lots of different types of rods. Different procedures, different fillet size, lots of different things. So an acronym we need to know is WPS. That stands for welding, procedure, specification. So, on your bigger jobs, stuff that matters, like buildings, stuff that people's lives depend on, a welding engineer is going to write out a WPS. He's basically going to tell you exactly how he or she wants it done. Okay, so on there it's going to tell you what process you're using. Let's just say SMAW tells you, they tell you what rod, E7018, and the size. They'll tell you the preparation they want on the weld. You know, they'll say, okay, we got a joint here. We want a 60-degree bevel or a 30-degree bevel, whatever it might be. They're going to tell you how many passes. So let's say 6 passes. Everything you need to know about the weld is going to be on the WPS. So just be aware of what that means. You're going to see that a lot. WPS, welding procedure specification. For things that don't really matter, you know, if you're building stuff at home or you're building, you know, non-structural items, you might not have a WPS. Just depends on the company you're working for. Okay, so this is the very, very basics of stick welding. We'll go more and more into detail the further we get into it, but this is kind of the very basics of how it works. In the next section, we'll talk about rods, what these numbers all mean, and then the section after that, we'll get into electricity. Okay.